Hello, everyone. We are going to talk in this section about Pascal's principle. This gentleman is Blaise Pascal, one of the best names, I think, in all of science. He was a French mathematician in the 1600s. He was a contemporary of Torricelli and Galileo. And when I say they communicated via letters, that's how they communicated across Europe in those period of time. Pascal was a child prodigy. He was so good at mathematics, he started publishing articles and things about math when he was still a teenager. And he was so advanced that a lot of people didn't believe that someone that young could actually produce something of that high a quality. But he had, and he produced a lot of great ideas in math and the physical sciences, meaning physics and chemistry, through the ages. So we are going to talk about one idea of Pascal's, and that is the concept of Pascal's principle. Pascal's principle says this, and put a star by this, make sure you know this. The pressure applied to a fluid is evenly transmitted to every point within that fluid. Now, what does that mean? That means that, let's say you have got a water balloon or something, or a balloon, something like this. If you squeeze on that balloon and apply pressure to that balloon, it is going to increase the pressure on every single point within that balloon, even the points that are far away from where you're actually squeezing. That's Pascal's principle. And there are lots and lots of applications of this, and we'll go into a few in a few minutes. But first I want to describe a demonstration that is theoretically done by Pascal back in the 1600s. Some historians say this never happened. Some historians say it did happen. Either way, it's a brilliant story about science, so I'm going to repeat it. And it goes like this. Pascal, like all scientists, had to have a way of funding his experiments. And so Pascal was being funded by the King of France. And every once in a while, Pascal had to show off a little bit. He had to prove to the King of France that what he was doing was worth the king's money. So Pascal set up a demonstration to demonstrate his principle of this transmitted pressure. And what he set up was this. He took a wine barrel, and inside of it, he inserted a long tube. Now, Pascal understood that pressure is related to the height of a column of fluid. So there's a direct relationship between pressure and height. So Pascal has this long tube, and then he has 1 additional cup of water. So he called up the king and all the courtiers to come around, and Pascal said, I am going to pour this 1 cup of water down this tube, and it's going to make this entire wine barrel burst. And so he poured the extra water in there. It rose the column of water just the necessary amount. The pressure got big enough, and that pressure was evenly distributed to every point inside of the wine barrel. According to Pascal's principle, the wine barrel exploded. Everybody was amazed, clapped, and Pascal was the hero of the day. But that is a brilliant story. At the end of this video, I'm going to ask you to watch 2 or 3 others of some of these really demonstrated in real life, some other videos. So please watch those. Here's another example of Pascal's principle. And these are your car brakes. Now, inside of your brake system on your automobile, you actually have fluid. You have brake fluid. And the brake fluid, if that poor person's sitting down, sorry, it's a weird angle, but when you push down on the brake pedal with your foot, what happens is this pushes on a cylinder, and that cylinder, when it pushes on the brake fluid, according to Pascal's principle, the pressure is transmitted everywhere within that fluid. So by pushing on 1 pedal here, you can actually apply a push to all these different areas within the car and make the brakes actually close so that your car will stop. Now, some of you have heard the concept of bleeding brakes. Now, if you have an air bubble somewhere in a brake line, what happens is liquids are not compressible. Gases are compressible. If you have a cylinder in an automobile engine or something like that, and you have gas molecules, and you compress that cylinder and you push it further down, what happens is the gas molecules become very close together and their density increases dramatically. That doesn't happen for liquids. So if you apply pressure to a liquid, the force goes in all directions. Well, if you have pressure coming through a fluid and all of a sudden you have air, what happens is the pressure stops being transmitted. What happens in your car? Your brakes are going to feel mushy. And that's in the best case scenario. The worst case scenario is you're going to lose your brakes and you're not going to be able to stop, which would be very, very dangerous. So when people talk about bleeding brakes, what they're talking about is actually removing the air bubble and replacing the entire line with brake fluid. Other examples of Pascal's principle. One is the famous beer bottle and mallet. So if you take a beer bottle, pop bottle, the cap has to be removed. And some people trying to be, I don't know, silly, will take one bottle, and if this bottle is open, they will hit one bottle with another and go bang. Well, if this bottle happens to be full of a carbonated beverage, what occurs is you end up with a shower of carbonated beverage all over the place. And as I have had many a student tell me, that is a waste of perfectly good beer. So you don't want to do that. But if after your bottle is empty, and the top, of course, is removed, if you fill this full of plain old water, something not carbonated, when I do this, I like doing it with a rubber mallet. And if you try this at home, please make sure you're wearing safety glasses. Make sure you are wearing gloves, because you are going to get some sharp glass out of this. But if you fill this quite a ways towards the top with water, smack it, a good smack with a rubber mallet, not a hammer, but a rubber mallet. Some people can do it with their hand. What happens is, because liquids are non-compressible, the push or the force goes all the way through the bottle, and because it hits the bottom, rebounds, and then goes back down and hits, it actually takes the bottom of the bottle and pushes it clean away. The force is transmitted through the bottle. Forces transmitted through a fluid, that is hydraulics, and it is a fun and simple little demonstration of hydraulics. Another example of Pascal's principle is a Cartesian diver. Cartesian diver, simplest example, is a 2-liter pop bottle with a little eyedropper in it, and if you've got your little eyedropper, put it into the bottle and put just a little bit of water in it, and here's how it works. If you push on the bottle, now the bottle is full of water, what happens is the push via Pascal's principle is transmitted everywhere in the bottle, including up inside of the little stopper or the little eyedropper. So when the pressure goes up in here, what occurs is more water flows up in here. This becomes more dense and sinks. When you release the pressure, the water flows back out again, and the little eyedropper pops to the top. Really, really fun little thing, but you need a 2-liter bottle and an eyedropper. Okay, let's talk about blood pressure. Lots of cool things in fluids with blood pressure. Question: why do they take your blood pressure around your upper arm? Why not around your wrist? Why not around your ankle? Why the heck do they do it around your upper arm? Well, remember that the pressure in the column of fluid is related to the height of a column of fluid. So medicine, they're most interested in the pressure in your heart, and your upper arm is about the same altitude as your heart. That's why they want to take the blood pressure at that location. They take it somewhere lower, like your wrist or your ankle. The higher the column of fluid, the more blood pushing down on those lower extremities, the bigger your pressure is going to be. So here's another blood pressure question. When you go to the doctor and they are going to take your blood pressure, they always ask you to uncross your legs. You don't want them crossed at the knee. You don't want them crossed at the ankle. So why is that? Well, that is back to Pascal's principle. Because of the fact that if you are pushing one artery or veins on another set of arteries and veins, you are increasing the pressure. And if you increase the pressure in a column of fluid or a body of fluid, and that includes your whole vascular arterial system, the pressure is going to go up everywhere, including the blood pressure in your heart. So if you cross your legs, you are going to have a higher blood pressure reading. I had a student a couple years back come to me and say, how do they take the blood pressure of a patient that does not have arms? And I didn't have an answer to that. So I asked one of my colleagues who happens to be a nursing instructor, and the answer is brilliant, and it's really, really fabulous science. And here's what they do. They ask the patient to lay down, and they put the blood pressure cuff around the ankle. Well, as long as everything is at the same altitude, if the heart is at the same altitude as the ankle, then the blood pressure readings will be the same. And it is a perfectly scientifically accurate and logical way to do that. So what we've been talking about in some of these systems is the concept of hydraulics. Now, hydraulics is the transmission of a force through pipes and tubes using a fluid. And basically, they all function using Pascal's principle. Lots of hydraulic systems in big diggers and dozers and things like this because there are so many forces involved. Human being can't manhandle those around, so they are full of hydraulic forces. Hydraulic lifts, if you go to the garage and they're going to put your car on a lift to change oil or something like that, you're going to have a hydraulic lift somewhere as simple as when you go and get your hair cut. And the cosmetologist or barber is going to be back here pumping on the little lever to get your chair to rise to or lower to the right altitude for them to cut your hair. That actually is a hydraulic system. So here's how hydraulic systems work. They work, again, because of this concept of Pascal's principle. So there is a shared chamber of fluid, and the pressure is going to be the same everywhere within that chamber. There is an input cylinder. Typically, the input cylinder is going to be relatively small. And then there is an output cylinder, typically relatively large diameter. And because they share one reservoir of pressure, the pressure is going to be the same for both. So here's how this works. Pressure is force divided by area. So the area, the cross-sectional area of this cylinder, divided into the force that must be applied here, is going to be equal to the cross-sectional area of this cylinder and the force that is the output here. And that, because pressure is the same, this is going to equal that. And that is pretty simple stuff. So the mathematics for that is also pretty simple. When I was first learning about hydraulics, I said to myself, this has got to violate, or it looks like it violates the law of conservation of energy, but it doesn't, because the work input equals the work output. The input cylinder, you have a small amount of force, but you have to move it through a large distance, x. Output, you get a big force output, but it's moved through a very small x. So the total work, force times displacement, of the two are the same. And I always go back to the getting my hair cut example because it's the one that I make sense out of. If I'm sitting in a chair to get my hair cut, the lady who's cutting my hair, she's pumping like a crazy person back here, and she has to pump maybe 10 times to get my hiney to move like an inch because of the fact that she has to put in a little force but over a big distance to move all of me a very, very small amount. But that is Pascal's principle, and we will see you later. Bye-bye.